Hello all. In this video we're going to explore the basics of the beam search algorithm. This is an approach that's similar to hill climbing. It kind of does multiple hill climbing channels at the same time, but it's based on the basic idea of why do we need to only have one starting point? Could we do better if we scattered random starting points across our search space so that we're searching more of the space at any one time? So beam search does exactly that. It creates a population of states and then it updates them step by step in a very hill climbing kind of way. All right, so our goal here with beam search is to improve the likelihood of finding the global maximum by searching in multiple places at once. And the fundamental, if you ask me for a one statement about what this does, is that we have k states. K is a variable you can change. It's a parameter you could tune to try to get a number that runs quickly but yet works for your problem. So we generate k different states at random. We look at all the neighbors of all of those states. We pick out the k with the highest values from the fitness function, from the objective function, and we keep the top k, and then we repeat the process. And we just keep iterating until we start hitting maxima and see how it happens. So the goal is that we shift away from less promising regions to more promising regions of the space. So if we have our points and they're all evenly scattered across like this whole space, I'm going to pretend my fingers are different points in this space. We have all of these points that we're following. We do some evaluation, and these are all the neighbors of our current states. And so we get these two that are right at the top. Those would be the two that we would pick to keep going with. Generally speaking, with beam search, we have a relatively small population size. K tends to be on the order of 5 or 10 or 20. This is different from genetic algorithms where we often have cases where we might have 100 in our population or more. All right, I have a high-level version of the beam search algorithm. I'm going to talk through it quickly, and then we'll go take a look at pseudocode in just a moment. So as I said, the number of beams is a parameter. It's something that we can input and tune as we wish. And this is really just an elaboration of what I said before. We generate n, or k, random states from the state space. We have our loop that's just like the other algorithms. We loop until we decide we're done. We create a list that's going to hold all the neighbors of all the current beams. So, and the beams is the terminology that gets used for these n different states that we're keeping track of. So for each state that we have in our set of n, we're going to generate neighbors of that state using hill climbing or stochastic hill climbing methods. We'll generate neighbors and we add them to the neighbors list. Then we pick the n best neighbors in the overall list, and that's our new beams, and we go around and do it again. What I'd like to do is to go back to our visualization of the state space and the objective function, how that plays into it. So remember, we're imagining that we've got two dimensions to our state space, and the vertical dimension is the value of each of these points by the objective function. So we have hills and valleys. There's a valley right here, and there might be plateaus and various things like that. So imagine that our 5 initial states that we generate for beam search are shown in the red dot. So this one's part way up this hill. This one's at the foot of the big hill. This is in the valley between the different hills. There's one here on the side of this hill and one up on the plateau. What does beam search do? Well, the first thing it does is for all of these, it's going to generate all of its neighbors, or some subset if you're using a variation. And so what I've done here is just to show 3 or 4 neighbors for each. So each state has some neighbors. Some of them are better, some of them are not. These are all meant to be lying in a valley in between the front hill and the back hills. But you can see some of them are going up the hillsides, and of course the plateau has generated neighbors that are elsewhere in different places on the plateau. So we have all of these neighbors. What we do is to look at over all of them, which ones have the highest value by the objective function. We select those out. So I'm going to mark the ones that I think are the highest value with this picture. I've marked them in green. So the ones up here on the plateau, that looks like it's higher to me than they say this point, but maybe this point and this point are the other two that are next highest in the overall space. We pick the best 5 because we had 5 initially, so we want 5 the next time around. These 5 become our new space. What do you see happening here? Well, points that were in low-lying areas that didn't have very good values, they're getting eliminated. We're not going to continue searching at those locations. Instead, we are targeting our search at a couple of other locations, and at the most promising one, just because it is more promising than the others, we are duplicating. We now have multiple points in that space, and we can search in the search will expand in this area while it's diminishing or decreasing completely in some of these others. That's the strength of beam search, is that we can generate these multiple neighbors in the places where it looks like it's the most promising. Now, of course, we said this over here is the global maximum in this particular diagram, and so this beam search is absolutely not searching in the right place. That can still happen. It's possible that we might make our way over to this area of the space at a later round, if we're lucky. All right, so here is the algorithm for beam search. It's pretty similar to the high-level one that I showed you before. We set up this nodes array that's going to hold our k randomly generated states. We loop until we're done, just like we do for the other algorithms, and we're going to set up a new list or priority queue of successors. And then we're going to loop over each of these nodes, generate its neighbors, generate its children, add those children to the successors list, and then choose the top k out of that successors list to become our new set of nodes. That's all very simple. If you think about this at all, we were worried about hill climbing being expensive. Beam search is really expensive. It can be really expensive. Especially if we look at all possible neighbors, and as we said before, if you have a lot of neighbors, or if your evaluation function is extremely expensive, this is just multiplying that. So instead of tracking one state, now we're tracking k different states. It can be a problem. So what we do often is we look at stochastic variations on beam search, and one option, which I think is discussed in the readings of the textbook we're using, generate all the children and evaluate them all, but then choose the k-best using roulette wheel selection. This allows just some randomness to go into the mix. You don't have to, you could do this without generating all the children. You could generate some number of children per beam, per node that you have, the states that you have. So instead of generating all children, you just generate 5 children for each state that you have. But you could still use this sort of roulette wheel selection, the resampling method, to choose among those children. But you could also use one of the methods like the stochastic hill climbing methods, where you generate a certain number of children for a current state and just keep the, not actually stop as soon as you generate something that's better than the current state. There are lots of different variations for beam search. All right, so you can see again, beam search is a little more different. It's still doing hill climbing as its basic approach, but it's adding in this idea of a population, and it allows us to retarget the search based on what states we have that are getting high ratings. And that can allow us to search the space more broadly. So the main thing that beam search is addressing is this question of finding the global optima. It's the optimum. It's trying to find the global optimum by searching more broadly through the space. In the next video, we'll take a look at genetic algorithms. What's funny to me is that genetic algorithms did not come out of the same community necessarily as the people who were developing local search, and it has a very, very strong drawing of ideas from natural selection and biology. And yet, it's actually really similar to beam search. There's this coming together of ideas that is actually a really interesting thing to see. I will see you all very soon.